In this lecture, I want to go through two reactions of benzene. These are the sulfonylation and nitration, sulfonylation, and nitration of benzene. So in this reaction, what we're doing, the sulfonylation, is we're treating our benzene with H2SO4, and I like to make note that this is very concentrated to the point that it's fuming. And what we get when we treat this with fuming H2SO4 is we form a benzene sulfonic acid. Turns out this is very acidic. It's actually kind of useful because it's a way to provide a strong acid to a reaction without introducing water. I know water is a byproduct of this reaction if you try to balance the equation, but you can isolate this from the sulfuric acid, and then you've got a way of introducing a very acidic proton into an environment without bringing water along for the ride. Whereas if you think about H2SO4, HCl, HNO3, we typically come with a lot of water. So this is kind of a nice, useful thing. Okay, so H2SO4, first of all, is sulfuric acid. We can draw sulfuric acid with an expanded octet, and it's a helpful resonance depiction because everything has a neutral charge. Whoop, goodness, has a neutral charge. Okay, so let's go ahead and jump right into the mechanism. Turns out there's no real opportunity for R groups here except if we put those on the benzene ring, which will be the focus of future lectures. Like, what if we do all these reactions with benzene having substituents itself, like toluene and that sort of thing. We'll worry about that later. For now, we're just using benzene, and we really can only use fuming sulfuric acid, so there's just sort of one reaction. Okay, so when we're fuming, step one, electrophile formation. When we have fuming sulfuric acid, we have an equilibrium to consider. I mean, I guess we always do. It's just a more prominent equilibrium when we're so concentrated. But when we're fuming, we're actively releasing SO3. SO3 is not great because SO3 reacts with water and makes a H2SO4 in the rain clouds, and then it rains down sulfuric acid, and that is the definition of acid rain. This is also called a SOx. If you think about NOx and SOx, we'll be talking about those today. Those are important industrial pollutants to be aware of because they can lead to acid rain. So what we're doing in the lab, and hopefully not in the sky, is worrying about this equilibrium where what we do is we steal an H and an OH from H2SO4 to make sulfur trioxide, or SO3, plus H2O. So SO3 is observed when sulfuric acid is highly concentrated. When H2SO4 is highly concentrated. That is to say when it's fuming, okay? So we're releasing SO3. You can see this equilibrium. If we release a little bit of SO3 in the presence of a ton of water, we're going to push this equilibrium back to make H2SO4. Not great. Okay, it sucks. Okay, so, and this is also called a SOx, an SOX, where the X is a subscript for various oxidation states. So SO3 is one example. All right, anyway, SO3 is a great electrophile. SO3 is also a great electrophile. And what that means is that when benzene sees SO3, it's going to react with it like it reacts with any great electrophile. It's going to add to the sulfur atom. And we can't take on that many electrons, so we have to push something up. We're going to push some electrons onto an oxygen atom to give rise to an SO2 with an oxygen singly bonded to sulfur, and it's now negatively charged. The carbon that accepted the sulfur is going to have, we're going to draw that hydrogen explicitly, to let us know that the neighboring positive charge can be dealt with by losing that hydrogen. Now, where's that hydrogen going to go? Well, our cationic complex is much more acidic than even some of the strongest acids because we would like to establish aromaticity. It's no problem. The SO3 minus will grab that hydrogen atom and make a fairly strong acid, but not as strong as a protonated benzene to give us our benzene sulfonic acid. Mechanism complete. It's the only possibility for this reaction unless we have a substituent on the benzene. This is the only mechanism then, again, unless we have a substituent on the benzene. Okay, so there's our product. We didn't really form a superelectrophile. We just considered it in equilibrium with the H2SO4. So H2SO4 can provide a nice electrophile for us. It turns out another important kind of common acid can do the same, and that's HNO3. That will lead us to the nitration of benzene. So in the nitration of benzene, what we do is we take our benzene and we react it with HNO3 to form a nitrobenzene plus H2O. Now, HNO3 is nitric acid. And the NO2, this is our nitro group. That's why I was worried about naming things with the nitro group, because we can actually make them now with benzene fairly easily. Okay. So what we do to accomplish this reaction is we take, first of all, let's go ahead and label this appropriately. I'm going to propose the mechanism for this reaction. And again, other than substituents on benzene, this is the reaction. There's no changing anything on the nitric acid component. Okay, so mechanism. First step is form the electrophile. It always is in electrophilic aromatic substitution reactions. So we have HNO3. Let's go ahead and draw a Kekulé structure of that. Now I'm just looking through. I have this nice rule. I just want to make sure I'm not off on this. For the mechanism of this reaction, I try to give you hints and that sort of thing to keep in mind. The mechanism for the nitration reaction is the N is always positive. Throughout the entire mechanism, the nitrogen atom is always positive from the start of forming the electrophile to the end of the reaction, because if you recall, the nitro group is kind of a funky thing to actually draw a Lewis structure of. So it's always got a positive charge on nitrogen. Okay, so here's what we're going to do. We're going to let nitric acid react with an N plus. Now, where did we get an H plus? Where did we get an H plus from? We got that from some nitric acid floating around. Okay, so we have H plus encountering our nitric acid. And you're thinking to yourself, I know where that's going to go. That's going to go in the negative charge. Negatively charged oxygen. And you're right, it does happen. And it happens many times. But when it does, when the negative charge on that oxygen atom reaches out and grabs the positive charge of the hydrogen, we're not going to get anywhere. Okay, but it happens all the time. It's just reversible because it's not going to go anywhere. Instead, what we want to consider is the other times that are not as frequent, but are very much possible, where the OH reaches out and grabs the H plus. I know that oxygen's negative. The other oxygen is negative, and it turns out by resonance, you can make the NO double bond also negative. Okay, but it's this one that gets us somewhere. So what we're going to do is we're going to protonate the oxygen that already has a hydrogen to give us something that's really close to water. Now, when that happens, when the H plus bonds to that OH, we're going to have an oxygen with a positive charge, but that can soak up the electrons from the nitrogen being positive, to form H2O. So do you see that? We have H2O here, H2O there. So H2O is a great leaving group. It makes water. Now, why would the nitrogen want to give up electrons? It's already positively charged. Well, that's where I rely on another arrow to come down, and that's the O minus to come down and make another nitrogen-oxygen double bond. So it's going to give us an NO double bond this way and an NO double bond this way. And when you look at it, that nitrogen doesn't have any lone pairs of electrons. It's only got those two things attached. So it's sp hybridized and we have to draw it linear. Just like with the acylleimine, we have a linear geometry. Now, what am I forgetting in this? Oh, the nitrogen is always positive. But didn't it just accept electrons? Yeah, it accepted electrons from the lone pair, but it pushed off the water in the same step. The nitrogen is always positive. And this is our super electrophile. NO2. NO2 is not great either because NO2 can react with water in the reverse of this process to make nitric acid. And so NO2, being a gas, if we release into the atmosphere, is going to make some nitric acid, and we have another source of acid rain. That's why they call it NOx and SOx. NOx and SOx as our common pollutants that can lead to acid rain. But we're not making acid rain, we're making molecules. Okay, probably releasing some stuff that could lead to acid rain, but we're doing it on paper. Okay. So we have our super electrophile that's going to encounter, and they have ways of trapping these things. Back when acid rain was an issue, we just didn't have ways of trapping these things, and we thought, oh, Mother Nature can handle it. Okay, so here the benzene pi bond is going to attack the nitrogen atom, and you're like, great, neutralizes the positive charge. But we can't exceed the octet, and that nitrogen already has 8 electrons if you look 2 double bonds to oxygen. So we have to simultaneously push electrons up and onto the oxygen. That's going to give us this structure where the the O now is a negative charge. We still have a double bond down here. H plus, now what am I forgetting? Oh, the N is always positive. Turns out that at this stage, we've actually completed the NO2 nitro group. That's what the nitro group looks like. You can push the electrons down and over to make an alternative resonance structure where you've got the opposite O being negatively charged. But the N is always positive and it has at least one double bond, one single bond to oxygen atoms. Okay, but now we're at where we're usually at. We're at the intermediate of our electrophilic aromatic substitution reaction, where we just lose the hydrogen that was attached to the carbon atom that gave rise to, or that formed the bond with, the nitro group. Nitrogen's always positive. We have H plus. H plus can be used to make more of the NO2. Is it catalyzed? I wouldn't go so far. Maybe, but let's just stick with this. Okay, but now we've made a nitrobenzene. You know what? Just for added measure, for added instructional measure, I'm going to draw the 2 resonance depictions that I was alluding to just for clarity. We have negative charge come down, negative charge go over. In both cases, the nitrogen stays positive. Okay, so key things with this mechanism to check your work, make sure the nitrogen is always positive. Okay, well, for the most part, what we're going to do going forward is studying these reactions, the halogenation reactions, the Friedel-Crafts reactions, sulfonation, and nitration. We're going to study these reactions in the context of more complicated benzenes, not like overly complicated where it's crazy looking molecules, but like what happens if you try to do a nitration with methylbenzene or chlorobenzene? So you've already done one of these reactions, you want to do it again, what'll happen? So that's what we're going to do going forward. So all of the reactions for this unit on aromaticity are already presented to you. So study up on these mechanisms, the halogenations, the Friedel-Crafts reactions, both alkylation and acylation, along with sulfonation and nitration. These are the mechanisms you need to know, and you won't see any others. Okay, so next time we'll look at some more complicated benzenes just with added substituents and see if we can figure out how these reactions proceed. So until then, I'll see you next time.